Good morning, everyone, or good afternoon on your local situation. My name is Jim Chastain, and welcome to the EasyPower Thursday technical webinar. Before we get started with the material and before I introduce our guest speaker, we'd like to run a quick poll question, and we would appreciate your feedback. Obviously, there's no obligation. What we're trying to do is understand the measure of the audience interest in the topic and make sure we have the right focus during the presentation on those various interests. So the bottom line is it focuses on filter design today, harmonic filter design. And because this is a complex situation that few of us face frequently in our career, there are different ways to kind of present it or focus the material. So if you could provide the feedback, please do so at this time. Well, I messed it up. Let's try this again. I still messed it up. Well, my apologies. I'm having technical difficulties. And we'll try it one more time. Well, so here's how we can do this. I prematurely aborted the controls for the poll. And unfortunately, I feel it's fairly important. So let me see if I can record them or restart it before we get going. Okay, one more time. Worst case, we'll ask people to respond on the chat line. So here's what we're trying to achieve. The choices are how to choose component ratings, number one. Number two is how to design filters based on EasyPower outputs. Number two is how to control protection considerations, deal with control and protection considerations. Number four is how to determine the filter type, whether it's a notch, a C, HP, or an HP. And then the fifth choice is other information, general information. If you would please enter your interest on the chat line, and we'll see if we can't collect that as we go along. I apologize for a double click. So Paul, we're going to let people respond on the chat line. My apologies for technical difficulties. So let me introduce our guest speaker at this point. Coming to us live from upstate New York with over 25 years experience in the topic is Mr. Paul Stusek. It's all yours, Paul. Let me hand off this presentation podium here.
All right, hello everyone. Welcome to this webinar series. I've done this quite a few times now. I'm Paul Stusek with Northeast Power Systems, NEPSI. For those who do not know who NEPSI is a manufacturer of metal closed harmonic filter banks and capacitor banks. We actually build this equipment here. We build this enclosure, and we populate the enclosure with basically the L, R, and C parameters that come out of your harmonic studies. So typically harmonic studies are often about determining the performance of a harmonic filter, choosing the LRC parameters, the type of filter, the tuning point, and the kVAR, but it very seldom gets into the details of what it takes to design and build a harmonic filter. That's what NEPSI does. There's a few of us out there that do this. The metal closed solution has some advantages in that it contains all switching protection and control. And that's what you're looking at here, a relatively large harmonic filter system that was put into a mine application up in British Columbia. This one is rated 23 megabars and it's a 25 kV system, 5 stages. Those boxes you see on top, everybody always asks, well, what are they? They are high pass filter resistors. They oftentimes have very high kW output, and therefore we put them in stainless steel enclosures up on top, and that's what they are. They're naturally cooled resistors. The metal closed filter or any type of filter system, not only are there L, R, and C parameters, there's also many other devices that go into the filter, PT, CTs, disconnect switches, ground switches, metering system, protection control, fusing, how to protect the filter, how to control the filter, and these are various topics that we can talk about when we talk about designing harmonic filters. Today we're going to focus on picking LRC. How do we pick LRC? And really, when you do a harmonic study within EasyPower, what it gives you is the performance of the filter. It tells you what the resulting voltage distortion will be within the plant that you're doing your study on. It will tell you what the harmonic current flow into the network is for IEEE 519 compliance, but it will also tell you the amount of harmonic current that might flow into a harmonic filter here. And with that data, you still need to produce a specification, an LRC specification. What capacitors, what voltage rating, what fuse rating, what reactor ratings should I be telling the manufacturers to build to? Because what you have done is you created a study, you got the results look great, but you still have another big piece of the puzzle to put together. And that's what we're talking about today. And it's important to understand, well, why is this important? Why is it important to be able to design a harmonic filter? You've done your study as a consultant or as an EPC, and that's great that the study is completed. If you, at that point, leave or if you decide not to go to the next step and specify a harmonic filter, what often happens is the harmonic filter supply becomes the responsibility of the major nonlinear load supplier, whether it's a arc furnace, a cycle converter, or a VFD drive. Oftentimes, consultants and EPCs will push that responsibility onto the drive supplier or the supplier of that nonlinear load equipment. And part of it's because they do not understand harmonic filter design. And as a consultant or as an EPC, if you can take it to the next step and specify the harmonic filter, you will be doing your client a great service. The reason being is that a harmonic filter like this here, it can be marked up by over a factor of $500,000 as a margin stacking by the drive supplier or by the rectifier supplier. Because in the end, if they're supplying the rectifier, say they're supplying a large LCI drive, for instance, they're going to stack margin onto the project for that harmonic filter design, and you're captive as the end customer because they're supplying that system. So in the end, it would behoove you, and you would be doing a great service to your clients to do this type of design work. Our website has guide form specifications. There are design tools on our website. There's how-to videos. We've done quite a few for EasyPower. And of course, if you call in, we have what's called NEPC reactor compensation sessions where we actually will go through and help you with the design. In the end, it's your design, it's your specification. We will bid to the specification on a competitive basis, but we can help with the design concepts that are required for these harmonic filter designs, even provide preliminary drawings and budgetary pricing. So let's get started with the presentation. Harmonic filters, what do they do? The first thing that most people do not realize is their primary purpose is correcting power factor. Oftentimes, the harmonic filter is rated to correct the system's power factor, and oftentimes that is the #1 rating that is considered when coming up with a harmonic filter. So you're doing you're doing power factor correction, #1. #2, you're looking to reduce harmonic current and voltage distortion. Sometimes it's to meet a 519 or some other type of industry standard for harmonic distortion. You might have a grid code compliance that you're looking to comply with. So you're doing a harmonic study to determine the filter design, and the filter is being designed and put in place to serve that purpose, either to reduce voltage distortion within the plant or to improve the current distortion, or what current distortion is being injected into the source, into the electric utility. And then sometimes it's also to prevent harmonic resonance. We need to do reactive compensation. We've already established that that's oftentimes a requirement, but when reactive compensation is implied, if it's just a capacitor bank, oftentimes that capacitor bank causes resonance, and we at that point will look to prevent resonance, and we install this harmonic filter to prevent resonance. Okay. What is a harmonic filter? It's essentially a reactor, okay, a reactor in series with a capacitor bank, and we're creating a low impedance path is what we're doing, and it's that simple. The reactor is typically a fraction in terms of the reactance ohms. The ohms of the reactor is typically a fraction of that of the capacitor, And in a sense, it means that the major component of power output is reactive power, and that's the purpose of it. When you think about harmonic filters as a specifier, you have an option. Do I specify metal closed, or do I specify open air? And there's two types of systems. They're significantly different. A open air filter system, you can see it's a rack structure. It's elevated. It's elevated because people can come in contact with live parts, and it's using air core reactors. The metal closed solution does not use air core reactors. That's a key difference. It uses iron core reactors. So we're going to talk about those two types of reactors during this presentation. There's also what's called an E-house configuration. Again, looks very similar to a metal closed system, but the difference is you're walking into an E-house. You walk into an E-house, which means that the components are spaced out on the floor, and you're walking around these various components to get to them. There's only one or two access doors, as you see here, and this is one of the major drawbacks to an E-house solution, is that there's only one or two exits. And I say exits, and that's a key point also, is that a E-house solution has exits, and it means that people can go inside, which means that the E-house has to be built according to local and national building codes, and that makes the specification of that type of harmonic filter that much difficult. The metal closed solution is built according to industry standards, IEEE, IEC standards, and so forth. You're following electrical standards, not building code standards that change depending upon your location. So key filter ratings, we've already established reactive power is a key filter rating. And what I have done here is I've put a standard nameplate for a typical harmonic filter system that we have. These would be the typical parameters that you would see on our nameplates, where it's specifying the L, the R, and the C components, their voltage ratings, their microfarads, and so forth. This kind of will help you develop a data sheet if you're developing a specification, because these are the types of parameters that you would ask the suppliers who are potentially bidding on such a project. So reactive power is the three-phase output rating of the harmonic filter. You also have its voltage and its insulation level. What voltage is the applied voltage to the filter, and then the insulation level, the BIL level of the harmonic filter, withstand level. These are based upon the voltage rating of the system. If you have a 34.5 kV system, typically that's going to be a 150 kV BIL per standards. So you go to the standards and you determine, well, what is the BIL and withstand voltage for that voltage level, and that becomes the insulation level for your system. You may increase that because of dust or pollution, but you're starting off with a base value that's based upon standards. You may have to derate if you're in a high altitude area for altitude, but again, you're starting off with a BIL and withstand level based upon the system voltage that you're at. The tuning point is something that you're going to specify, but that tuning point has come out of your study. You've done a harmonic study, and that tuning point comes out of it, and that's something we're going to talk about. And then in the type of filter, C high pass type filters. We typically have a fundamental current rating, which is basically related to the reactive power rating of the system. Okay, whatever the reactive power rating is, we have a fundamental. You want to account for a 10% over voltage condition. There is a possibility that you will have a 10% over voltage, so all filters should be designed assuming that you have that 10% over voltage condition assumed. And then harmonic currents. You would want to specify all the major harmonic currents associated with the filter. So you've done the harmonic study. The harmonic study has determined the harmonic current flow into the filter, and you will specify those. But what I want to make sure is clear is that when you specify harmonic currents, you do not just take the data from the study and then give that to the supplier of the filter, because that means the values are too small. Typically, you want to be at a level that is quite significant in comparison to what your study has come up with. The reason being is that the system and what goes on in the actual system may be different than what goes on in your study. You may have assumptions that you have made. There may be more harmonic current in the system. There may be ambient voltage distortion within the supply voltage. All these will contribute to adding harmonic current to your filter. So it's very, very important to over-specify the capacitors and the reactors and the resistors and assume higher values. And we're going to talk about that in a moment, some of the philosophies that we take when we do this. So how do the filter ratings get determined? So the reactive power is typically determined based upon a load flow analysis. You've done a load flow analysis and you have determined that you need a certain amount of reactive power. That forms a key basis for determining the reactive power rating of the filter. The other thing to think about is if you have a multi-tuned filter, and I'm jumping ahead a little bit, if you have a multi-tuned filter, you have to partition the reactive power across multiple tuning points. Well, partition the reactive power across those multiple tuning points based upon the harmonic current that is expected to flow into that filter. If I have a 12-post drive, for instance, it consists of a significant amount of 11th and 13th harmonic. I know I need to put in a 5th, 7th, and 11th filter. Okay, the 5th and 7th are being put in, not because there's a lot of 5th or 7th harmonic present in the system, but because the 11th filter will result in a possible 5th or 7th resonance. So I'm putting in a 5th filter, I'm putting in a 7th filter to filter this 11th, this 12-post drive, but I'm putting those 5th and 7th filters in to prevent resonance from going on. But the majority of harmonic current in a 12-post device is at the 11th. So I need to make sure that I put a lot of reactive power at the 11th harmonic. The ideal situation is that when you are all said and done and the system is operating at full load, peak load, that the harmonic current that flows into a filter branch is no greater than 50% of the fundamental. So it's a good rule of thumb, no more than 50% of the fundamental. So whatever the reactive power rating of the filter is, the harmonic current that flows into it, an ideal design will be 50% of the fundamental. And in the end, the specification, you specify 100% to the reactor supplier, to the capacitor supplier, or to the harmonic filter supplier. You make an assumption that, well, it could be 100%. In so doing, what you have done is you've created a bulletproof design. You've created a filter that will never fail because you've designed for the worst case condition and it's at 50%. You still have another factor of 50% of margin to take care of things that you have not accounted for. So the filter component ratings, you can use harmonic analysis programs to do that. We at NEPSI, we will use a spreadsheet tools. We have a spreadsheet tool on our website. I highly suggest you go and take a look at it. It's at resources / spreadsheet tools. That tool we use to calculate the L, R, and C parameters. Okay, so essentially the spreadsheet tool asks for how many megabars at the 4.8 tuning point do you want, and from there you can specify the capacitor and the reactor ratings. They will come out with those parameters. In fact, we have inserted into that spreadsheet tool a snapshot of the filter parameter input that EasyPower has, and we auto fill those values so that you can then reinsert those into the program. So it's a two-step process. The program is determining the LRC parameters based on the performance of the filter based upon the data you put in there. But you have to have a starting point. You have to say, well, I need a 5th filter. I need it to be 5 megabars. I take that 5th filter with 5 megabars. I come up with L, R, and C parameters. I put them into EasyPower. I look at I determine the performance of it, and then I determine the amount of harmonic current flow that flows into that filter. I take that harmonic current flow, I put it back into the spreadsheet, and I calculate the performance of the various components that I have chosen. And this is the process. It's an iterative process. It doesn't happen magically. So some harmonic filter basics. I've drawn an equivalent circuit to what you see here on the right. So I have a simple source transformer, and then a very simple system. And up here on the top left, I've drawn the equivalent circuit. So what's the harmonic filter do? It takes the harmonic current injection that's here, and it diverts some of the current into the filter. The filter must be able to handle the current flow, that harmonic current flow. Any kind of current flow through an impedance, as indicated here, 2 pi FL, the current flow through there must be handled by that reactor in that capacitor. So this is the basis of what the spreadsheet tool does. Is it says, okay, I know what the harmonic current flow is. Let's make sure my voltage rating and my capacitors are correct. Let's make sure I specify the harmonic current rating on the reactor correctly. So this is the procedure. So the filter offers a low impedance path, and I kind of indicated that down here with the impedance scan. This red line indicates the equivalent impedance of the network Actually, the red line represents the impedance of the harmonic filter. Okay, it's a notch tuned harmonic filter, it has a low impedance at the 5th harmonic, meaning that any harmonic current flow that comes from this harmonic current injection is going to flow into this filter. And it's also interesting to note that some 7th harmonic current would flow into it, of course, because it's an impedance divider. Current flow at the 7th harmonic at this location, we're going to have some harmonic current that will flow towards the source, and then some that will flow into the filter. And this is what the program is doing. It's calculating that harmonic current flow. But what's important is you take that harmonic current flow, put it back into a spreadsheet tool, and from there you can calculate what the resulting performance is. So there are 3 major types of filters. These are almost, I would say, 98% of the harmonic filters that are specified in the industry. The first filter is a notch-tuned filter. It's on the farthest left. It is the most simplest filter, and it's a preferred harmonic filter that is used, and it's because it's simple. Generally speaking, you're starting at a low frequency, like the 5th. The lowest, most prevalent harmonic current in the network is the one that you're starting with, and you're tuning from there and go and onward and upward. Generally speaking, you want to use single tuned filters if possible. They may be multi-stage, but you still want single tuned harmonic filters if you can, and that's because of reliability purposes. Only go to multi-stage, multi-tuned harmonic filters when the system dictates. So you're going to go multi-stage because you sometimes need to divide your reactive power up into chunks because you're trying to track power factor within the plant. You're going to go multi-tuned because you can't get the performance out of a single tune notch filter. You go to a multi-tune notch filter. If you still can't get the performance, then you start to think about, well, I'm going to go with a high pass filter or a C high pass filter. And the high pass filter has more losses. It's more complex because it has a resistor in it. And for this reason, it has more cost and you try to avoid it. But sometimes your system will require this type of harmonic filter. And then lastly, we have this C high pass filter. A C high pass filter carries the same performance as a high pass filter. The difference being is we have this aux capacitor right here in the middle, and that aux capacitor acts to tune this inner branch, this X or L here, this inductance and this capacitance to 60 hertz, when we therefore are shunting this resistor and eliminating losses at the 60 hertz rating. So we have an increasing cost for these types of filters, and it only makes sense to start with notch filters. So the impedance profile for a notch filter, as I show it here, is a preferred filter. It's got a low impedance point, almost 0 ohms at its tuning point. Almost 0 ohms at its tuning point. It drops right to 0. The X over R for a iron core reactor is typically about 100. So in EasyPower, when you're inputting the X value, it's going to want a value of resistance in ohms, and it wants a value of inductance or reactance, inductive reactance in ohms. You would take the inductive reactance and divide by 100 to come up with the resistance of that reactor. If it were air core reactors, if you were in fact specifying an open air solution, it would be about 60. So there's high pass filters also, and you can see there's an impedance profile associated with the high pass filters. Depending upon the value of resistance here, the value of resistance here will change the shape of the curve. Obviously, if we were to take a resistance value and make it infinite at this point, very high resistance, it would become a notch filter. And that's kind of what you see here. This blue curve is the high pass filter approaching a notch filter. So generally, especially in EasyPower, it's very easy to flip back and forth between a notch filter and a high pass filter. And it's actually nice the way it works. You put in your notch filter. If we got some type of problem, you can put in a value of resistance and turn it into a high pass filter, and then you can just increase or decrease that resistance to get the performance you want. In the end, the question that often comes up is, well, what's a reasonable value of kW? So kind of another rule of thumb to think about is, if I'm putting this resistor value in here, you may have a desire to continue to decrease this resistance to reach some type of performance. As a general rule of thumb, a value of kW losses in a medium voltage filter, and I'm talking about filters between 2.4 kV and 38 kV, no more than, let's say, 150 kW per phase. That's a lot of losses, but if your filter design requires more than 150 kW losses per phase for this resistor, then you have to find something else, or you should start looking for something else. And there's a cost associated with that, so you want to try to avoid that. One of those things to do is to think about a C high pass filter. If I had to decrease this value of resistance so far and my losses have gone up so much, a lot of that losses will be associated with 60 hertz losses, and a C high pass filter will eliminate that. The spreadsheet tool we have will give you the parameters for resistance for these parameters, including this value down here. EasyPower does not have a internal model for this. It's one of those things that EasyPower should think about doing, is getting this type of filter in, because it's quite common. So you have to build a filter from scratch. There was another presenter, I think from 2 years ago, that presented how to input a C high pass filter in there. So if for some reason you need to come up with the modeling for a C high pass filter, then you can go back to that presentation presented by that gentleman. It was a very good presentation. The thing that really is important to note, though, and is of interest, is if you can use a standard high pass filter like this in EasyPower, come up with a performance, go to the spreadsheet that we developed, and develop your specifications for it. You do not need to repeat the study with the C high pass filter, and that's because a C high pass filter and high pass filters have the same characteristic curves. So the only difference is you're not doing a final check within the program. It's just an extra step. You might ask the question, well, why high pass versus notch? This is oftentimes the case, and it's best to show it with a sample of a system. On the left, we have a notch filter application and 3 notch filters. It's a multi-tune harmonic filter. Now on the right, we have 3 C high pass filters, same megabar ratings. The difference is that we added the resistors and created high pass harmonic filters. If you look at the impedance characteristics, what you see is that we have a resonance created by the notch filters. The blue curve is the notch filters. Those resonances can cause problems if I have harmonics at these locations, which is common for some nonlinear loads that produce non-characteristic harmonics. So when you have non-characteristic harmonics within a plant, in this case, like say 6th or 7th or 8th, and this might be, or that would be 8th or 9th, not the 7th, that's common. It would be likely that you would consider a high pass type filters, because you're looking to dampen the resonant condition, okay, at these locations. Common for cycle converter type projects. You may also be looking at putting a filter in and you have cable capacitance, and oftentimes we will see this in the renewables area. The collector system is so large, there's capacitance in the network, and as such, there's resonance that exists at the higher frequencies, and a high pass filter can dampen that resonant point out here. We've eliminated this resonance out here with a high pass filter. So the calculation methods is noted here. I don't have a whole lot of time to go through all this in detail, but these are the formulas. This data was presented for a 1000 kVAR, 4.7 tune, 13.8 kV. We go through all the steps here. I'm not going to go through the steps because there's a little bit of detail there. The important thing to note is that when we are doing these types of calculations, us at NEPSI, we are not going through this detail each and every time. We go to our spreadsheet tool and we plug in the values and we get the data. It's that fast. It really takes about 2 minutes to develop a harmonic filter design. Technically even less than that, about 1 minute. So it's a very fast process if you develop a spreadsheet tool. You have to first learn to trust the spreadsheet tool. We've been using our spreadsheet tool for about 25 years and we trust it very much. If you come up with values that are different than what our tool comes out with, more than likely there's something wrong in your calculations. We oftentimes will get specifications sent to us, and the L, R, and C parameters are wrong or different than what we're calculating. We go back to the customer and say, hey, listen, your parameters seem to be a bit off. So it's a good basis. We lock up the spreadsheet so that you can't change the formulas, and therefore we know that the integrity of the program is correct. We have also yeah, a high pass filter calculations here, and the procedure for coming up with the X of L value here and the X of C value here is exactly the same for a notch filter as it is for a high pass filter. It's exactly the same procedure, same formulas. The only thing that changes is the resistance. How do we pick the resistance? The resistance in a high pass filter, C high pass filter, is always done by trial and error. You put in what's called the damping factor to come up with a value of R based upon damping factor. And do I even show it here? Yeah, damping factor here, the DF value. And that determines how flat the curve is. Generally speaking, you go with a high R first, you start to decrease R until you get the performance you want. From there, you would calculate your losses. And again, you can do that in EasyPower, but you can also do that within the spreadsheet tool itself. And then you have C high pass filters. The procedures are very similar, again, for calculating the tuning point. What's interesting on a C high pass filter is X of CA equals X of L, which means that the terminal voltage here has been brought down to here. We've eliminated the voltage rise according to at the fundamental, because X of C and X of L are opposite each other. You have a plus J and a minus J, and therefore we've eliminated the voltage rise from that capacitor. We've more or less brought the terminal voltage to the inner capacitor bank. This value of X of C, okay, is taking up most of the voltage within the system and creating the reactive power. So again, the spreadsheet tool is here. To design a harmonic filter is really just these yellow values here: voltage, megavars or kvar, tuning point, system frequency, X over R of the reactor. Just assume 100 because that's what it typically is. You pick a capacitor voltage, and then from there we're checking the parameters. Does our parameters meet the industry specification for that element? Okay, and we're going to talk about that component selection and rating. And we're going to talk about capacitors, reactors, and resistors. The first thing that is really important to note is that you want to be conservative in your ratings. You are going to pay pennies on a dollar for conservatism. When you go to a reactor supplier and you're getting a reactor quoted, increase your harmonic current flow more than you think, because it does not cost a whole lot to increase that harmonic current flow that reactor might be asked to do. Your system may change. The customer may add drives in the future. There may be unexpected off-system resonance or resonance between your filter branches. If you have added the rating into the equipment, you've put conservatism into your design, you will not have a problem after it's installed. We have, especially early on with NEPSI 20 years ago, we used to design filters more tight and we had more problems. If you design a harmonic filter and you have a lot of conservatism in it, you're guaranteed not to have problems today and into the future. So shunt power capacitors, we're going to talk about capacitors, then the reactors, and then the resistors. So the power capacitors follow some standards, and almost all medium voltage banks we're using 2 bushing capacitors here. This 2 bushing capacitors are single bushing capacitors, but they're single phase capacitors. They all follow the standard 18. There's a standard C22, but it basically mirrors standard 18. And that's the 2 standards you'd want to go to if you're developing a standard for North America or a specification for North America. Then you have IEC 60871 for the IEC type applications. But again, the premise behind it and the values that you're checking against in your design are nearly the same. So what's going on? We have developed a model in EasyPower. EasyPower has told us, okay, based upon running a summation all, what the harmonic current flow is into the filter bank, right? It's a series circuit here. We know the harmonic current flow into the filter. you need to evaluate, well, how does this harmonic current flow through this capacitance? How does it impact the capacitor? What voltage rating do I need, and what kVAR rating do I need to specify to meet the requirements? So this is what you're basically comparing to. You're doing 4 points of evaluation. You're saying, well, what is my RMS voltage? Well, we can calculate 60 hertz voltage very easy here, and you got to calculate your harmonic voltage also. Well, I have a fifth that I've calculated from the program. I know that fifth harmonic current flow. I know X of C, right? X of C is 1/5 of the value of what it was at the fundamental. I can calculate the voltage there, and I calculate an RMS voltage. The standard says, the IEEE standard says that you should not exceed 100%, 110% of the rated voltage. What's really key here, though, is there's that 10% here. We already have 10% that we need to allocate for over voltage within the network. Remember, systems can run plus minus 10%. So the 10% that's allocated for over voltage conditions cannot be taken. So really, we cannot develop a harmonic filter using a standard capacitor based upon the system voltage. We need to go to higher voltage to account for the harmonic voltage rise on here, plus the fundamental voltage rise across the reactor. So you're picking a capacitor that's going to be within this 110% RMS voltage rating based upon your harmonic flow, based upon a system voltage running at 110%. And you then pick your voltage rating, your capacitor based on that. There's also some other parameters that you need to check, and that is your peak voltage. Okay, so all the harmonic currents flowing into your capacitor can be coincident, in other words, all in phase, and they can all add to what is called the peak voltage. You create the peak voltage. I provide the method of calculation here, and this is something the spreadsheet tool will do based upon harmonic current flow that you push into it. It will calculate, well, what is that V peak? Incidentally, this is normally the limiting factor. This is why we most often have to push the capacitor voltage up. We push the capacitor voltage up so that we remain below the 120% rated peak voltage. So now I've come up with two parameters. The last two is RMS current flow into the capacitor. It can be no greater than 135% of its nameplate rating, and the kVAR can be no greater than 135% of its rating. So these are the 4 parameters based upon the calculation that you're doing here, that you're comparing to. And you go into the spreadsheet and you bump up the voltage. It's an iterative process. You keep bumping up the voltage, which bumps up the kVAR, and you do that until you meet these minimum requirements here. And then you're taking a off-the-shelf capacitor and you're applying it into a harmonic filter. When you're looking at capacitors, there are different types of capacitors. This happens to be a data sheet put out by Cooper. There's what's called standard duty, heavy duty, and extreme duty. And you're going to pick if one of these ratings. You need to know that if you go to ABB or to GE, that you may have a different over voltage capability based upon the duty of the capacitor. When you're thinking about capacitors, you do not need to specify a standard rating. We show here the standard ratings: 300 kVAR, 400 kVAR, 500 kVAR, 600 kVAR. If you go to a capacitor supplier, they are not going to squeeze you into a 300 or 400. You can buy a 332 kVAR capacitor. They are not going to charge you more for that capacitor. They're going to charge you for the capacitance that they put into it. By buying a special capacitor does not mean that you're going to pay a higher price for it. You basically pay a pretty competitive price. A 350 kVAR capacitor will have a cost that's in between the cost of a 300 and a 400 kVAR standard capacitor rating. So pick the capacitor rating based upon what you need for your design. We don't need to get into discharge. All capacitors have an internal resistor built into it. They all discharge in a 5-minute period per standards, unless it's specified otherwise. And think about capacitor rating. Typically, we're looking at between 500 and 600 kVAR. For metal enclosed, we like to use very large capacitors. Why? Because we like the enclosure to be small. But you always have weight to think about. This 667 kVAR capacitor weighs close to 125 pounds. So think about the weight of the capacitor. But the more capacitors you add, the more cost you have, and the larger the enclosure or larger the open rack structure. So think about what that's going to do. Our preference is always to go with a smaller design, less capacitors, larger cans. Capacitors need to have some type of protection. The typical protection is blown fuse detection. We show that here. We have a neutral unbalanced protection system that's pretty standard, but we can also do fuse sensing here and check for the fuse itself. We can actually determine, well, what is the fuse, is it in operation or not? And we can do blown fuse detection with direct fuse sensing. When a fuse operates, it's important that you realize that the tuning has changed in the network. So you have to have a protection in there that says if a fuse operates, I'm going to have to take the stage off because my tuning point has shifted, or I have to increase the number of capacitors to allow for the failure of one capacitor. What's really interesting to note though is the failure rates for capacitors are like 1 in 5,000. If you properly choose the capacitor, your failure rate will be very low. For tuning reactors, and I show here an iron core reactor here. For tuning reactors, there are some standards. There are no direct standards that dictate the tuning reactors. My recommendation is to always go to a reputable tuning reactor supplier. In the United States, I only know of 3. In Europe, I know of 1. So there's not a significant number of those. You want to make sure they understand what a harmonic filter reactor is, and that they are a regular supplier of filter reactors. And this is especially true for iron core, but it's also true for air core. So I put down the suppliers for air core and for iron core reactors here. For tuning reactors, we have iron core on the left, and we have air core on the right. The key difference between these two is the iron itself. The iron is like a transformer. It carries the flux. It keeps the magnetic field inside the core of the reactor, and therefore there's no external flux. The system is very compact and is well suitable for metal enclosed systems. You can't put an air core reactor inside a metal enclosure because it will heat the walls up because of the external magnetic fields. These are very large. Oftentimes they're stacked 3 high. But another key difference is air core reactors do not saturate. Iron core reactors do. The reason why iron core reactors will saturate is because they're underspecified. They're underspecified. So if you specify them correct, iron core reactors will never have a problem. They will act and behave and have the performance level of an air core reactor. So we compare the differences between iron core and air core, and really magnetic fields is one of them. It tends to be that iron core reactors are more competitive in cost than air core reactors, and this is true up to a point. Remember, to create inductance with an air core reactor, it takes a lot of turns. It takes a lot of copper to create ohms, and that's what tuning reactors are. They're ohms of impedance. So it tends to be that iron core reactors are more competitive to a point, and as the megabar rating of your filter goes up, or as the tuning point goes up, the inductance goes down. And at some point, there is a crossover where an air core reactor might be more competitive. So a picture of an iron core reactor. It's this is a very large iron core reactor. It's very heavy. So whenever you're thinking about even having to remove one of these from an enclosure, it can be quite costly. And this is why it's important to specify conservatism into the iron core reactor, because to remove it while it's in operation or while it's in the field is a difficult situation for the customer. So specifying it correctly is important. We would typically for iron core reactors use single phase reactors. Those reactors are put up on insulators here, and what we do is we tack the core to the winding, and what we do is we elevate the reactor core in voltage. And we're doing that because under normal operation, the voltage drop across the reactor is 1 over the tuning point squared. So typically that's almost low voltage. For a 5th tune reactor at 13.8, that might be just 300 volts. So it's very small. So if we do that, most of the voltage stress is across the insulators here, and therefore very easy to design for, and it makes for a very inexpensive and very reliable harmonic filter reactor. You can have three-phase reactors. Three-phase reactors are more difficult to design. They have their limitations because they can get quite large. Because there's three phases, you would have to then ground the core, which means we have full voltage stress between the winding and the core. So typically these are available up to 13.8 kV, and it's difficult to get a 13.8 kV fifth harmonic filter reactor greater than 2 megabars. So we have some limitations in what can be done. So single phase reactors obviously are more reliable because we're dropping the voltage across an insulator, very easy to design for, versus a three-phase reactor where we need to be worried about phase-to-phase voltage here on the same core, and also phase-to-ground voltage here. The reactor supplier must wrap the Nomex between the core and the first winding enough to withstand the system voltage, and that can be quite costly. So in tuning reactor design, what the major concern is, well, what is the harmonic current flow through the reactor? You have a 60 hertz voltage drop here. The core is being designed to withstand that, and the winding is being designed to take that current. But then we also have the harmonic voltages and harmonic currents that are being created here. On the right here, I showed the ratings table. This is what we supply our reactor supplier. So it's very simple. There's not a whole lot that they need to quote a reactor. Just they need to know the number of phases, system voltage, the impulse level, if there's any taps for tuning, for tolerances purposes, and they need to know the inductance in the system frequency. So the specification of a tuning reactor is very simple. And I forgot to mention, we have the harmonic current into it. So again, air core reactors, we can see here they're quite large, right? They're quite large and oftentimes stacked. So there's a whole discussion about, well, the differences between air core and iron core and their advantages and disadvantages. And we're talking about magnetic clearance requirements here. So then finally, high pass filter resistors. The calculation procedures are listed here and here. We have two sets of calculations. Again, what's determining the losses within the resistor is primarily the voltage drop across the reactor, both fundamental and harmonic. We can determine what the voltage is here, and it's just a matter of calculating V squared over R. So it's a very simple calculation. Spreadsheet tool does all this. We recommend a factor of 2.0. Whatever your KW rating you come up with, we recommend a factor of 2.0 on that. The resistors are a grid type design. And here again, I recommend that you always go to a reputable supplier. In the United States, there's Avertron and those Post Glover would be the only two that we would recommend here that we know of. We recommend a grid type resistor, stainless steel grid, and not this winding type of resistor because it can carry inductance. Here's a close-up of how that resistor looks. So that kind of completes the presentation. I did buzz through this pretty quick because I have a hard stop at 2 o'clock. I do encourage people to check out the spreadsheet tools and also to reach out to me. I stress that having the ability to specify harmonic filters is a plus for your organization. If you're involved with consulting or EPC work, you will save your clients a significant amount of money by taking the filter design responsibility from the possible supplier of the nonlinear load devices.
Paul, this is Jim. Thank you very much for the presentation. We're running short on time. I suggest that we do a follow-up Q&A via email so that all the questions, and there are a number of them, get answered. And there was one question that I guess intrigues me as well, and that is, how do you do the spotlight focus on your presentation?
That's a secret. No, it's called it's a Logitech device, and it's called LOGI. LOGI. And I do see there's some questions that came in, and I would be happy to answer any of the questions. If there's somebody with some doubts, I'm okay with that. If they want to ask me those questions. I do many filter designs every year, and I have a pretty good insight into harmonic filters and their design and their performance and whether it can be built or not. And I encourage anybody who's involved with harmonic filter design, if they got any questions, send an email to sales@nepsi.com or to my email. I kind of dropped it on the bottom of this presentation. We'll be happy to answer them. I've been a EasyPower user for 25 years. I know the insides and outs of the program, at least from a harmonic analysis standpoint, quite well. So I can also kind of assist with that stuff also.
Anything else you want to touch on?
No, I'm good. I think I'm good.
All right. Thank you very much. And thanks to all the audience for attending. And there's a survey at the tail end as you leave that you can ask specific contact information, and Paul or EasyPower can follow up. Paul, thank you very much. Good talking to you again, and we'll be talking to you down the road.
Yeah, great. I'll see you. Thank you.
Bye.
Bye.